Com check, com check. Okay. Uh, 12:30, and we have three students in attendance. Okay. Four students. Getting better. My office was so loud on campus yesterday, had to uh, I had to head home early so I could get something done. They had a little hoe ram inside old chem. You know what the Bobcat version of a track hoe, and then they had a hoe ram on that, and they were running that, and then they would bring in a Bobcat and scrape out the debris, and so it wasn't even like a constant noise that you can kind of ignore. It was 2 3 minutes of hoe ram, and then a couple of minutes of debris falling 3 stories down into a dumpster, and then yeah. So I had planned on being on campus this week, and that's just a non-starter right now. All right, let's get started. Everybody else will catch up soon enough. So here we are, Tuesday, October 24th, live class session number 19. Formally appreciate Maggie taking class on Thursday last week and doing a demonstration of TSD and then of ETABS. It would have been a little bit better if it were another maybe 2 classes away, but it worked out better with my own travel schedule so that I was able to make that work out. So anyways, here's my schedule for this week. I had office hours this morning, and then I have office hours again on Thursday afternoon. Kind of an odd timing based on what I've been doing, but in order to make that work with some meetings that I have tomorrow, that's probably the best I can do. Then looking at our overall, we have not too many classes coming up, not too many classes left. We have 1, 2, 3, 4, 5, 6, 7, 8 classes left before the end of the semester. So the end is near. And with that in mind, I'm planning the assignments that we have and the submittals that we have due for the rest of the semester. So I spent some time this morning posting some of these. We have homeworks 7, 8, and 9 that are now posted. I really only expect you to be working on homework number 7, but I know some of you have had some experience with this before and might want to work ahead. So I've gone ahead and posted a couple of those assignments. The exam that's on the week of November 13th, I've decided to go ahead and make that a take-home exam. It'll probably be something where I make it available at 12:30 on Tuesday, the 14th, and then have it due maybe Friday, what would that Friday be? The 17th at 5 p.m. or something like that. That way, if you happen to be traveling earlier in the week or later in the week, you still have a couple of days to work on it. All right, and then homeworks 10 and 11. I haven't assigned those yet. We'll wait and see how things go with our pace of the remaining classes. I definitely want to do homework number 11. You have an assignment where you guys are actively using ETABS. Homework number 10 is a good assignment to do, but if we're running short on time, then it's a one that I could sacrifice. There's a couple of others that I've given in the past too. How to do a buckling analysis in SAP 2000. So I have that assignment that we could explore as well. But my hunch is that we'll probably run out of time before we have a chance to really dig into that topic very deeply. Okay, so today our agenda is to do more two-dimensional modeling of the Tower of Terror in SAP 2000. And when we stopped last Tuesday, I had just introduced the idea of a joint constraint to capture diaphragm action in our structure. And so before we go any further in SAP 2000, what I'd like to do is present formally the idea of a joint constraint. Oops, there we go. And so I have this PowerPoint presentation. It's relatively short, but it discusses what a joint constraint is in theory and then how to implement it in SAP 2000. After we work our way through this, then I'll fire up SAP 2000 and we'll continue our discussion with some of the details associated with that particular modeling environment. All right, so You might remember at the beginning of the semester, I presented three different topics, three different definitions that are often confused. One is a restraint, the other is a constraint, and the third one is a release, right? A restraint is where we set 1 degree of freedom or some degrees of freedom equal to 0, usually 0. That's where the support structure, the structural supports are at, like a base plate or a bearing or something like that. A constraint is where we set degrees of freedom within a structure equal to one another. We might say that the horizontal degree of freedom at one node has to be equal to the horizontal degree of freedom at an adjacent node. Or we might say these degrees of freedom, a whole group of degrees of freedom, maybe the horizontal degrees of freedom at 3 nodes have to be equal to the horizontal degree of freedom of this other node. Then it's unfortunate terminology given our political environment now, but one of those nodes becomes the master and the others become the slave nodes. And that terminology persists despite despite its unpopularity with respect to the political ramifications of that. So, and then the releases, I think we have a good handle on those now. That's where we release the end of a member relative to the node that it's attached to, so that we can incorporate things like hinges against moment or torsion, or releases with respect to shear or axial force and those sorts of things. So the last of those we have to discuss is a constraint, and it's a set of relationships between joints. They don't necessarily have to be equal to each other. You can set an equation so that they're related to each other based on some type of algebraic formula. And the one that we illustrated in class last Tuesday was a diaphragm constraint, and in a two-dimensional model like the one we were doing, that algebraic formula is delta x at one node is equal to delta x at another node. But if we work in 3 dimensions instead, and we want this diaphragm action to work so that that floor slab is free to translate in 2 directions or rotate, but free to do so as a rigid body, then that algebraic formula becomes more complicated. We have to develop some sort of geometric relationship between the nodes so that the deformation of those nodes remains in a rigid body sense, so that they are all positioned relative to one another as they were in the unloaded situation. Now, luckily for us, this is something that SAP 2000 handles for us. We don't have to develop those algebraic relationships, but the algebraic relationships that are used in SAP 2000 depend on the type of constraint that we define, and there's a number of different ones that we'll get into later on here. You can do this in the matrix stuff. Either Thursday or maybe next Tuesday, I'm going to jump back and do the last of our matrix discussions, which is on frame analysis. And you can impose a constraint using those matrix operations, but that's typically something that I don't get to in that discussion. When we used to offer a full 10-week course on matrix analysis of structures, we would do that sort of thing. But nowadays, when I'm only having 5 lectures on matrix analysis, I don't get that far anymore. All right, so the types of behavior that we like to model are rigid body behavior, equal displacement behavior, or symmetry or anti-symmetry conditions. Sometimes it's more efficient to only model half of a structure so that the model size remains small, and then you can impose a symmetry constraint there such that all the displacements remain in plane like they would in a symmetric structure. And you guys, I think, talked about that a little bit in your undergraduate analysis courses, where you talk about how to make problem sizes a little bit smaller. So here are the others that I mentioned. A restraint defines a relationship between a node and an absolute reference frame, and a constraint defines a relationship between a node and another node. And then there's a release that allows us to incorporate things like pins and things like that. So these are the types of constraints that are included in SAP 2000. We have a rigid body, we have a rigid diaphragm, a rigid plate, a rigid rod, and a rigid beam. And so I'm not necessarily in love with the names that the people at Computers and Structures gave to these different constraint types, but this is what we have to work with. If you go into other packages like Abacus or ANSYS, they have constraints that we use all the time. and they go by different names in those packages, but they are basically the same types of constraints. You'll find out, I think, on the last slide of this presentation, that when we go and look at the other package that I love to hate, visual analysis, there aren't any constraints available in visual analysis, which is a serious limitation to that code. But visual analysis is what it is. I hate that, and I just said it anyways. It's a good low-level package for doing introductory level stuff. Let's hope the people from IES Web don't tune into this recording and then all of a sudden they yank our educational version, because I'm not entirely supportive of the package. All right. So when we use the constraints, it basically reduces the number of simultaneous equations that we have to solve. So if you start off with, say, 9 degrees of freedom in a model, and all of a sudden you say that degree of freedom 3 has to be equal to degree of freedom 5, then you've removed one of the unknowns from our system of equations. So instead of having a 9 by 9 system of equations, you now have an 8 by 8 system of equations that remains. And so that's one advantage to using constraints, is that it makes the problem size smaller, but more often than not, we're going to use constraints to model a condition that is model it academically or analytically in a way that's different than what it's actually portrayed in the actual structure. Most constraints are defined with respect to a coordinate system, either the global coordinate system or a local coordinate system for a node or for a member, or an alternate coordinate system that can be defined specifically for that constraint. When we looked at the diaphragm constraints on Tuesday last week and implemented them in our brace frame model, it automatically determined what the coordinate system was for those diaphragm constraints. All right, so here, the body constraint, rod, diaphragm, plate, beam. There's other ones here that I didn't include in the list before: equal, local, or welds. And so just working through these and taking the descriptions out of the SAP 2000 manual, body constraint causes all of the constrained joints to move together as though they were a rigid body. And so that can be useful if you're modeling the end of a beam, for example, and you want to connect the node at the end of a beam with a node at the column line, then you can use that body constraint to impose rigid body motion of that group of nodes to mimic a rigid connection in a steel building, for example. All degrees of freedom are connected. The subset of the degrees of freedom can also be defined. And this is used to model rigid connections where several beams and columns frame together. It can be used to connect different parts of a model that were defined using separate meshes. And it can also be used to connect frame elements that are acting as eccentric stiffeners to shell elements. We haven't talked about shell elements yet, but that's coming up soon as well. Okay, there's a rod constraint that causes all of the constrained joints to move together as a straight rod that is rigid against axial deformation. Effectively, all the joints maintain a fixed distance from each other, but translations normal to that axis and all rotations are unaffected. This can be used to prevent axial deformations in frame elements, and it can be used to model truss-like links. And this can actually be used to model diaphragm behavior as well. So here's an example of the rod constraint. This image comes out of the SAP 2000 manual, so that's why it's a little bit clunky. I didn't include a reference. But what we're doing here is we're imposing a rod constraint between these 5 degrees of freedom, the X translation at nodes 1, 2, 3, 4, and 5. And so what it does is it defines a master joint at some place. Maybe it uses one of those 5 nodes as the master. Maybe it creates a 6th node and uses that as the master. And so what that says is that the horizontal displacement at each one of these is going to be equal to each other. So you're going to end up with some displacement delta, and it's going to be the same at all 5 of those joints. So if you impose a rod constraint at each of the, let's see, 1, 2, 3, 4 levels in this structure, then that would be equivalent to defining diaphragm behavior for each of those 4 levels as well. So that works well in a 2-dimensional structure, but the actual diaphragm constraint that we'll talk about in a minute is a little bit more effective, a little bit more elegant in performing that. So if the axial deformations and beams are negligible, a single rod constraint can be defined constraining the 5 joints. Instead of 5 equations, the program would use a single equation to define the X displacement at that whole floor. However, it should be noted that the axial forces that result from that analysis in those beams is going to be equal to 0. So if you're worried about diaphragm forces, in-plane forces within the floor slab or the roof slab, then that rod constraint can give results that are not accurate when you go in and design those diaphragm members for chord forces and things like that. Okay, here's the diaphragm constraint. This is by far the one we'll use most often in this class. And it causes all of the constrained joints to move together as a planar diaphragm that is rigid against in-plane membrane deformations. All constrained joints are connected to each other by lengths that are rigid in the plane, but they do not affect out-of-plane deformations, either vertical deformation or a rotation. This constraint is used to model concrete floors or concrete-filled decks in building structures which behave with a high in-plane stiffness. They can be used to model diaphragms in bridge superstructures as well. And so here is a depiction of a 3-dimensional model where we have 1, 2, 3, 4 columns. And so what we've done is we've identified that each one of these joints here at the, I guess you could call that the roof level, is going to be part of a defined constraint that is defined as a diaphragm constraint. And so what SAP 2000 does is it defines an automatically generated master node or master joint, and then it generates relationships between the deformation in the X direction and the deformation in the Y direction, such that if this node here rotates or translates, that this node would also move correspondingly. And so that's very useful, very helpful in that everything is taken care of automatically after you define the constraint and assign the joints to that constraint definition. All right, the use of the diaphragm constraint for building structures eliminates the numerical inaccuracies that can result when you have large in-plane stiffness modeled using membrane elements. You could also use shell elements to model the floors or the roof. We'll do that. But sometimes, even if you have shell elements, it's nice to use a diaphragm constraint. It's also useful for lateral analysis of buildings as well. It results in a significant reduction in the size of the problem. And it has an added advantage in SAP 2000 in that it allows lateral loads to be applied much easier than in the absence of a diaphragm constraint. I'll show you this when we get to SAP 2000 later today, but one of the last things that we did in our model demonstration on Tuesday was we applied the lateral loads that were resulting from wind at each of the levels. And that's rather tedious to do when you apply them as nodal loads or as joint loads. When we use a constraint, it becomes much more straightforward to do that. I'll get back to that. Here's a plate constraint. Plate constraint causes all of the constrained joints to move together as a flat plate that is rigid against bending deformation. So this is a little bit different than the diaphragm constraint. With the diaphragm constraint, it's rigid in plane, but all of the nodes are free to do whatever they want to perpendicular to that plane. The plate constraint is basically the opposite of that. Everything is free to move around in the plane of the plate, but when it goes to out of plane deformations, then they are constrained. This can be used to connect different types of frame and shell elements to solid elements. Solid elements don't have rotational degrees of freedom at their nodes. So this constraint can be used to connect a rotational degree of freedom from one node and pair it as a pair of translational degrees of freedom at other nodes. It can also be used to enforce the assumption that plane sections remain plane if you do a detailed model of a beam using shell elements or solid elements. Here's a beam constraint that causes all of the constrained joints to move together as a straight beam that is rigid against deformation. So this is the 2-dimensional equivalent of the 3-dimensional plate constraint. If you only have it working in 2 dimensions, then you can use the beam constraint instead of the plate constraint, and it's analytically a little less computationally expensive. So the analysis, the analogy could be created between a beam constraint versus a plate constraint relative to a rod constraint and a diaphragm constraint. So in 2 dimensions, you could use a rod. In 3 dimensions, you use a diaphragm. In 2 dimensions, you use a beam. In 3 dimensions, you use a plate. Okay. Again, similar to what we just discussed with respect to the plate constraint, only working in 2 dimensions. Then there's an equal constraint. This one is interesting. It basically sets the constrained degrees of freedom at adjacent nodes equal to each other. And so it's not like a rigid body constraint where if we had, say, 2 nodes and they were constrained using a rigid body, then they might move up like this. And so that would be a rigid body translation between those 2 nodes. Instead, if you have the equal constraint and both of these nodes rotate, then what tends to happen is this node moves up to here, and then this node moves up to here as well. So the degrees of freedom are actually equal to each other as opposed to moving as a rigid body. And so let's see, there's no coupling between rotations and translations. This can be used to partially connect together different parts of a model, such as at expansion joints or at hinges and things of that nature. For fully connecting meshes, it's better to use the body constraint when the constrained joints are not exactly in the same locations. Here is a local constraint. Local constraint causes all of its constrained joints to move together with the same displacements for each selected degree of freedom taken in separate joint local coordinate systems. The other degrees of freedom are unaffected. Doesn't use a fixed coordinate system, but references the local coordinate systems instead. There's no coupling between rotations and translations, and it works out to be the same as an equal constraint if all of the constrained joints have a local coordinate system. So this can be used to model symmetry conditions. It can be used to model displacements constrained by mechanisms. So let me go and illustrate. So let's suppose you have 2 nodes, one here and one here. And now we define degrees of freedoms for these nodes. Maybe that's the 1 degree of freedom. Maybe that's the 2 degree of freedom. And then that's the 3 degree of freedom. Over here, then you could have that perhaps as the 1 degree of freedom. That's the 2 degree of freedom. And then that's the 3 degree of freedom. So you could set displacement in the 2 degree of freedom over here equal to displacement in the 1 degree of freedom over there. That would be the same as an equal constraint. Or you could go and set the 2 degree of freedom there equal to the 2 degree of freedom there. I don't really know where you would use this, but it's available if you come up with some kind of an academic problem where that would be useful. Then you have the weld constraint, and this works much like you would think. You can weld 2 pieces of a model together using this constraint. And it consists of a set of relationships for the joints that are going to be joined, such that the weld shares the same location in space as the constraints to the single joint. So the program automatically determines which internal master joint for each explicit constraint and the master joint for each internal body constraint that is generated by a weld. Each master joint governs the behavior corresponding to the constrained joints or to the slave joints. And the displacement at the constrained degree of freedom is computed as a linear combination of the displacements at the master joint. So when we go in and look at these in SAP 2000, the process that we use to implement a constraint in a model is we have to define the constraint first, and then we have to assign the joints to the constraint that we defined, to the constraint that we defined. So we're going to go in most cases, we're going to say we're going to use a diaphragm type of constraint. And then we go in and we assign the nodes that we want to be constrained to the diaphragm constraint that was defined. And the way that you do the first step is you go into the define menu, joint constraints, and then you can define which type of constraints you want and which of the options you want to include. So most of the time we construct our SAP models such that the z-axis is the vertical axis. So the perpendicular axis is going to be the z-axis. It's the axis that's perpendicular to the diaphragm that you're trying to model. You could also use a diaphragm constraint to model a wall, I suppose, if the wall was rigid. And in that case, you might want to use the x-axis or the y-axis to define the constraint plane instead. Or if you have a bunch of nodes that you're going to assign to this constraint and they are in a plane already, then SAP 2000 will determine what that plane is and then automatically determine what the constraint axis should be. There's this option down here at the bottom that's usually quite helpful. If we have 8 floors in our building, then in theory we would have to define 8 different constraints, 8 different diaphragm constraints. But knowing that that's something that we're commonly going to do, the SAP 2000 included that option where it will automatically create 8 constraints or 1 constraint for each of the Z values of the nodes that are assigned. So that's also useful. And then those of you who have done some work in practice know that these diaphragms are often rigid, but sometimes they're not. Sometimes they're semi-rigid. And so what defines a semi-rigid diaphragm from a rigid diaphragm is a topic for another class. But basically, if you have a concrete deck, either a monolithic concrete slab in a concrete building, or maybe a concrete filled metal deck, that's going to be rigid in almost every case. On the other hand, it's not uncommon for steel buildings to have metal decking with insulation board on top and use that for the roof where there's no concrete. And that might be flexible enough that it can't be considered rigid or shouldn't be considered rigid. And so in that case, you could define that as a semi-rigid diaphragm, and then you could model the characteristics of that appropriately. After you create the diaphragm constraint, then you actually go in and assign the joints to that constraint that you want to have appropriate. And so here we see the floor 2 constraint that I just defined. All right, and then I mentioned already earlier that SAP visual analysis doesn't include constraints. It's not an option. So, all right. ETABS does, of course. ETABS is basically just a tricked out version of SAP 2000. So just about every option that's available in SAP 2000 is available in ETABS in one way or another. And I think all of the what I would consider to be the top shelf analysis packages have constraints included of one form or another. Like you guys know by now that I've really dug deep into SAP 2000. I haven't dug nearly as deep into many other packages, but all the best that I've worked with do have diaphragm constraints or constraints of some sort. All right, let me stop sharing here. Any questions at this point while I kind of shift gears over here to my other computer? Let's see. I thought I had SAP running, but I don't. Why? But it takes a minute to launch. Even though I have a commuter license on this computer, it doesn't have to go to the license server, which is nice because then I don't have to run the VPN when I don't want to. There it is. All right, so here's SAP 2000. Let me go ahead and open the model that we were tinkering with the last time, Tower of Terror 2D brace frame. All right, so this is the same model that we were playing with last time. I haven't done anything to it since we worked together last time. Let me go in here. I want to show you the loads that we had on here. All we did was define the wind loads, and I set them up as a nodal load in this model. So let's go ahead and show those. You can see, I know it doesn't come out very well, but you can see these arrows here. Let me get rid of the grid. Where is that at? There we go. Now you can see perhaps a little bit better. So I went in and defined those as nodal loads, and it became a little bit tedious to do that because I had to go in, select each node, then I had to type in the right value of the load, et cetera, et cetera. Let me go over here for a second. I want to, in this model here, let me get rid of the grid too, by the way. View, show grid, Control D, I should remember that. Let me go in, I want to show the nodes, make those visible. And then, let's see, hit apply. There, the nodes come in. Now I want to go up here in that window. I want to show miscellaneous object assignments, and I want to go in and show the constraints. And so I can go in and show each of these diaphragm constraints. And so what it does is every node that's assigned to the diaphragm constraint at Z equals 100 feet just turned green, right? And I could do the same thing. Here's the diaphragm constraint that was automatically defined at Z equals 50 feet, right? And it looks like that. All right. Now, one of the benefits to this is in how we apply those lateral loads. So let me go in here to define. I'll go to load patterns. Let me do something a little bit strange. I'm going to define a new wind pattern. I'm going to call it wind DIA instead. And it's going to be a wind load here. And now I have the option of applying an automatic lateral load. And so what I'm going to do is go down here to user defined. I'm going to hit add new load pattern. And then I can go in and modify the lateral load that's assigned to that. And what it does is it gives me this convenient table where I can now go in and specify force in the X direction, a force in the Y direction, or a moment about the Z axis at each of the levels for which a diaphragm constraint was defined. That was a mouthful. So now, instead of going in and defining these loads one node at a time, I can go in like this, quick and easy, and define my diaphragm loads really. Whoops, I didn't. Darn it. Really easy. Yep, right. Just like I just said. So let's see, 21.2 there. And I hit, yep, it's really easy. Here we'll go, let's see, 23.9. Hit the down arrow twice, 23.3. This is going to be 22.6. This is going to be 21.8. This is going to be 20.8. This is going to be 19.6. And then the last diaphragm is 18.2. And if I do that, hit OK there, and now I can go in and run my analysis again. It's going to give me results both from the wind loads that are defined as nodal forces, and it's going to give me results for the wind loads that are defined using the diaphragm constraints. Let me go in and look at the display shape. Over here on the left, I'll go to W, hit apply. Over here on the right, I'll go to WDIA, hit apply again. And what I hope is, let's go to inches here, skip inches, is that I get the same results. So here I get a displacement in the two direction of 2.305 inches. Over here, I get a displacement in the two direction, 2.305 inches. And so one of the best secondary benefits of having diaphragm constraints in the model is that it's so much easier to define lateral loads. And that benefit alone is almost worth the price of doing business with respect to these guys. All right, questions? Get a drink of water. All right. So what I'm going to do next is I'm going to try and take this model and I'm going to morph it into a three-dimensional version of this model. And so I'm going to save it using a new file name. I'm going to go in, save as, and this is going to be Tower of Terror 3D brace frame, or 3D frame instead, like that. Okay, so what I want to do then is I want to go over here and look at that in 3 dimensions. I hit the wrong one. That's fine. And let me bring the grid back in, view, show grid. And I need to edit that grid and expand it a little bit. Now, let me see if I can bring up my Tower of Terror definition. What day was it that we had class last? It was the 17th. There we go. That's the one I want. All right. So here's the typical floor plan. So I want grid lines in the X direction spaced at 32 feet is basically what I want. So I want to modify that. I'm going to go in here, add I need 4 of them. The ordinate there is 32. This is, we can go in and specify spacing instead. Shit. So this is 32, whoops, 32 feet, 32 feet, 32 feet. And I think that'll do it. Let me go back here to ordinates. And yeah, I think that works out just fine. Okay, hit OK. And there we go. Now I have that 3D grid. So what I'm going to do is I'm going to select everything that's in this first brace frame here. And I'm going to copy it over to the right. And so what I want to do is use the replicate command. And I want it to be in the X direction, 32 feet times 1, 2, 3 spaces. All right. That didn't work. Let's do this, 32 feet. And then I'll go back up and type times 3. Gives me 1,152 inches. I only want 1 copy. Hit apply. There we go. And so now I've got that brace frame modeled over there. Let me do this now. I want to look at framing line D. Let me zoom out here a little bit. That's not great. Where did it go?
Swanson, did that copy loads over too?
Yes.
When you replicated it?
Yeah, if you you can go in, let me, yeah, so if you don't specify anything else, it will copy loads over, which is not great for the lateral loads that I had defined on there, but if I wanted to define the gravity loads, that could be useful. All right, and what I want to do now is give an elevation view of grid line A. If I look at this, I've got grid lines A through D there. Here I've got them. Yeah, same. Okay, good. And so I'm going to go over here. I want to set a 2-dimensional view. And so what this does is it lets me define what view I want to look at. And so I want to look at the XZ plane at Y equals 0. And so what that's going to do is give me an elevation view of framing line A. Now, it doesn't show anything there because I don't have any elements or objects defined on that. Let me go ahead and show the grid in that view. And now you can see that grid pop up. Okay, so I'm going to define the moment resisting frame next. And I think I have those members defined for the moment resisting frame here. So I've got 12 by 190, 12 by 106, 12 by 58, and then the beams are defined as such. I think in the interest of time, I'm just going to define them all as the same beam and then let you guys go and modify your model when you do this as a homework. If I took the time to specify them each as the right beam, that would cost me most of the rest of the hour, and I don't want to spend that time doing that. So let me go ahead and draw in some members. I'm just going to use, let's see, what could I use for the columns? I'll go ahead and use the 12 by 72 as the column members. So I specify that column there like that. I'll go over here, do the same thing there. Then I'll go in and for the beam, let's see, I'll use a W18 by 55 for the beam and go like that. Okay, now this is going to be the lateral framing in that direction. So let me select those members. Okay, I'm going to hit Control R. I'm going to replicate that in the Z direction. So this is 12.5 times 12. And I want 1, 2, 3, 4, 5, 6, 7 copies of that. So 7 copies. Hit apply. And that gives me that moment frame. So now what I can do is select these guys again, and I can go in and I want this to be in the Y direction now. I want to copy from framing line A up to framing line B. So in this case, I want 24 times 12 times 3, 24 feet, 12 inches per foot, 3 bays. And I can hit apply, and then that, oops, I didn't want 7 copies. Oops. That's why they include the undo button. Where is it at? I just hit Control Z and get the same effect, I think. There we go. I only want 1 copy, not 7. I got to select those members again. Hit apply. Why didn't it go? There it is. Okay. Now, if I'm clever at this, I can use this as my model for the lateral framing. The rest of the members that go in here are just gravity framing. They're there to carry gravity loads down to the foundation. They're not there to resist lateral loads. If I'm clever, I can go in and I can select all of these joints and I can assign them to the joint constraint. Whoops, that's not what I wanted at all. I can assign them to the joint constraint that we defined last time. So I've got a hiccup though. I've got to delete those constraints first and then start over again. So let me go into my constraints, joint constraint. Let me delete all of these constraints. I guess I have to do it one at a time. All right, there we go. Now I'm going to go in here, diaphragm constraint, add a new constraint. The constraint axis is Z. I'm going to define a new one at every Z level that's selected. Hit OK. Now I can go in and assign joint constraints and then go to the diaphragm, hit apply. All right, good. Now when I go in and do my analysis, this should work. Fingers crossed. Even though this model is grossly unstable, having that constraint gives the model stability. It links the stability of the brace frames acting in the Y direction to the out of plane deformation of the moment frames in the Y direction. It links the same thing for the opposite direction as well. Let's see, I did get an error though. I think I forgot to define restraints at the bottoms of these moment frames. So let me do that. Let me pan this guy around. Need to define restraints at these nodes here. So we'll go to assign joint restraints. I'll just make them pinned. Hit apply. One other thing I forgot to do when I set my analysis options, I had it set for a plane frame. I need to go back and reset that for a 3D frame, like that, space frame. Okay, let me try this again. And so we get our results, no warnings pop up, which is good. And one of the things you can see over here in the left view is this series of nodes that's defined along the center of the building. And so it looks like those are, I don't know, graphics artifacts or something like that, but they're really not. Let me go in here to Control W. I want to show the labels on all of the nodes. And taking a while. It's probably going to overheat my computer. Come on. Oh, I know what I need to do. I need to do this, go to the undeformed shape. So those nodes are actually the automatically generated nodes that SAP uses as the slave nodes for each of those diaphragm constraints. So you see the tilde next to 201. That means it's a node that SAP automatically generated, and it's a node that it's using as the master node for the diaphragm constraint that exists at the roof level. And so this one down here is the automatically generated node that's used as the master node for the constraint at the second floor level. So that's what those are. And now if we go in and look at the deformed shape again, I'll use WDIA. Actually, I can't do that because I deleted those diaphragms and they moved away. Let's do this. Let's go back here to lateral load definitions here. And that's the slide I want. So I'm going to move that to another window so I can type these in faster. Let me kill this analysis results. And we'll go in here to define load patterns. WDIA. Let me delete this one now. We don't need that. And we'll go in and modify that one. And so in the X direction, that's the load on the moment frame. So I've got 15.4. I've got 17.0. Actually, no, I'm using the wrong loads. Let me correct myself. Let me go back to the spreadsheet that I was using. Here are the full values. I want these full values of these loads. I'm going to get rid of the ink. So I want to apply 23.7 instead. So let me fix that. Modify. Okay, so in the X direction, I want 23.7. I want 26.2, 25.5, 24.6. I want 23.7. I want 22.6, 21.1, and then 19.5, and then the diaphragm at the ground level. That's moot. At the Y direction, let's see, this is going to be 32.6. This is 36.8. This is 35.9, 34.8, 33.5, 32.0, 30.1, 28.0, and that's good. Now I'm applying these all at the same time. So I have my force in the X direction applied at the same time as my force in the Y direction. Let's go ahead and look at the display shape that we get from that. So what we can see then, if we go in and look at the deformation, whoops, structure is ill. Yeah, great. Nothing ever works the way I want it to. Let's look at my deformation there due to that. So we can animate that. I wouldn't want to rob you of the music that Sapman puts on it, which is pretty horrible. But you can see that it's moving and it's moving together. So the diaphragm constraint is holding everything together. All right. The next step in generating a 3D model for this would be to add in the lateral framing. And so what I want to do is, I'm sorry, add in the gravity framing, not the lateral framing. What I'm going to do next is I'm going to define the gravity framing at the in the first story and at the second floor level, and then I'm going to copy that all vertically. And so let me do this. I'm going to take a vertical view of this, a near vertical view. Let me look at the XY plane, I guess is what I want. All right, I'm going to select all of these nodes here, and I'm going to assign them to a group. And I'm going to define a new group, and that frame up there, what did I call that? Was that moment frame? In the definition, that was moment frame 1. So I have that frame up there on framing line D. That's going to be MF1. This is going to be MF2. This is BF1. That's BF2. So I'm going to create a new group. I'm going to call that moment frame 1. And then I'm going to assign all of the members and nodes to that group. I'm going to do the same thing down here. Let me get rid of that selection, get a new selection here. I'm going to define a new group, call that moment frame 2. Okay, hit OK, then hit OK again, then hit apply. Then I'm going to go over here and select these guys. That's brace frame 1. So I need to define a new group, add a new group, call that BF-1. Hit OK, and then I'm going to assign those to BF1. Then I'm going to go over here and make that BF2. Add a new group, BF-2. Hit OK. Hit OK again, BF2, and then apply. Close. All right, now what I can do is go into my view, and I can show some groups and not other groups. Let me see, where is that at? View. Now there's I should have rehearsed this before class, and I did. There's a way where you can remove those groups. Let me come back to that. I'm going to go back to a three-dimensional view over here. View, set 3D view, apply. Okay. This isn't working right. There we go. Now I'm going to look at the first story of framing. Let me go to view. I want to set my 3D view. I want to set the limits on that 3D view though. And so in the Z axis, I want to set my display options to show everything from 0 to 12.5 feet. I hit apply. And so that basically just shows me a 3D view of the first story's worth of framing. All right, I hit OK. And so I'm going to bring that up here, zoom in a little bit. And now what I'm going to do is define the gravity columns that I have. There's a gravity column there. And so then I can define one gravity column there like that. I probably should have defined them as the W section, but I didn't. Let's see, I'm going to take that guy, I'm going to replicate it. Let me work in feet instead of inches. That'll save me a couple of keystrokes. I'm going to replicate that guy. I want it to be in the Y direction, 24 times 3. I want one copy of it, hit apply. Okay, so that copied it over there. Now I'm going to select that guy and that guy. I'm going to replicate that in the X direction. This is going to be 32 times 3, hit apply. And now I should have columns at the 4 nodes. Yep, there they are. I'm going to do the same thing here at the center. I'm going to replicate that. DX, let's try this 32, 24. I think I have to do it one step at a time. So let me avoid that inevitable error. Then I can replicate that 0, 24. Apply. Okay, good. Now what I can do is put in the beams. And so let me do this. I'm going to define this over here. I'm going to go to a 2D view. I want to look at the XY plane at a value of Z equals 12.5 feet. Hit apply. And so that gives me basically the plane at the second floor level. So now I can go in and define beams. I'll go ahead and define it as 18 by 55. I'm going to use pinned. So now I'm going to define that beam like that. And now I'm going to replicate that. So if I go in and replicate that, come on. There we go. Control R. Let's suppose that I want beam spaced 3 beams per bay. So I'm going to space it at 8 feet. And then what I'm going to end up with is 1, 2, 3, 4, 5, 6, 7, 8, 9 copies of that. Hit apply. And you can see that it showed up in both views. Now what I can do is this. I'm going to select all 10 of those beams. I'm going to replicate it at a distance of 32 times 2. And then this is going to be 0. And I only want one copy. And then they pop up over there on the right where they're supposed to. Let me do this. I'm going to select these interior beams here. I want those to be copied at a distance of 32 feet with one copy. There we go. And now what I'm missing are the girders. Let me check this to make sure that I have the releases defined the way that I want them to be. Yep. And so each of those beams is pinned at its end. So it's released the way that I want. Let me go in now and define the girders. Close this. We'll just go ahead and use 18 by 35 girder, 18 by 55 girders as well. I want that to span between those two nodes like that. Let me adjust the properties of that. What I want to do is make sure that each of these frames is set up so that it automatically meshes at intermediate joints, and it is. You could also set up your other automatic meshing at this point too before you copy. Close. Let me go ahead, and now I'm going to take that guy and replicate it. I want that to go at dx equals 32 feet, and I want 3 copies of it. So that moves it over there. Now let me select just those girders. So I'm going to drag from right to left to select those 4 girders. I'm going to copy at a distance of 24 times 2. I want 1 copy. Hit apply. Okay, copies them over there. And now I've got the interiors here. That's going to be at a distance of 24 feet with 1 copy. Hit apply again. Close. And you can see now I have my girders. So now what I can do is I can select just about all of the members that are in this floor. I don't want to select the beams that are part of the moment frame, and I don't want to select the beams that are part of the brace frame. So let me go here to my view. This is where I wanted to turn off the members that are in the moment frames and the brace frames. Where is it at? Here it is. Select groups. Let's see. Brace frames 1 through brace frames 4. Let's select those. It's not working the way I wanted it to. Show selection only. View, show selection. Yep, that didn't work. All right, let's go back to plan. All right, I'm just going to select these guys by hand. 1, 2, 3, 4, 5, 6. Okay, I'm going to replicate those members. This is going to be in the Z direction at a distance of 12.5 feet. And what do I want? Do I want 7 copies or 8 copies? So I have I want 1, 2, 3, 4, 5, 6, 7 copies. Hit apply, and it looks like nothing happens because of the way I have my view set up. Let me go here to view, set the limits, and show all Z. Hit apply, and we get that. All right, well, that didn't work exactly the way I wanted it to. Still, hopefully this had some value. So if you're constructing a 3-dimensional model in SAP 2000, that's one of the ways to do it, is define one level of framing and then copy it vertically. This was a little bit convoluted because I already had the different levels within the 2D, within the brace frames and the moment frame set, and I ended up with some extraneous results here. I'm out of time. What I'll do is I'll take a few minutes and figure out what I did wrong and fix it, and then I'll start with that model the next time and show you the next few steps in this. All right, so that's it for today. I'll hang around for a few minutes to answer questions. I know that there was at least a couple people that wanted to chat with me after class. Otherwise, I'll see you in class on Thursday at 12:30, and then office hours on Thursday at 2:30.